Okay, Houston, as I stand out here in the wonders of the unknown at Hadley, I try to realize there's a fundamental truth to our nature. Man must explore. And this is exploration at its greatest.
Humanity is always pushing its limits in space exploration, from launching the first satellite into space to landing the first humans on the moon. Our curiosity for the far beyond has never been more realized. Now, we will tackle the next biggest step in space exploration, setting foot on the red planet. We are Georgia Tech, and this is our mission for an impermanent surface day to investigate our neighbor, Mars. Above all else, we wanted to prioritize the search for life, interoperability, and safety in this mission. At the top of our pyramid is one of the central goals for this manned mission, effectively performing the search for life. Upholding our most important goal is the interoperability between our systems. A synergistic approach to our mission architecture allows us to improve time efficiency, technical capability, and overall performance. Each of our systems are designed to work and fit with each other to carry out all the mission phases. Finally, safety serves as a foundation to successfully achieve the first manned mission to Mars. We wanted to make sure that every one of our architectural decisions was driven by safety measures to ensure the security of our astronauts. Overseeing all these goals was the drive to find a balance between ambition and feasibility. Mission Mars features cutting-edge innovations that will promote safety, mission reusability, and the search for life. An extendable rover design saves space, and its remote piloting capability allows the surface crew to focus on their science mission. This ability to drive without communications delay will provide an already set surface habitat for the next mission. Additionally, powered Mars gliders will collect useful atmospheric data that will aid in future landings. Finally, upcoming technologies such as torpor and various EDL techniques are integral to the success of this architecture.
There is ample opportunity for caution and reliability when designing a mission architecture, especially through foresight of potential failure points. Mission Mars avoids as many of these difficulties as possible by taking full advantage of launch dates and trajectories. Once launched, the crew imparts serious limits on mission duration and radiation exposure. The 30-day surface mission seems to hint at an opposition class mission. However, we opted for the conjunction class architecture, in part due to its launch date flexibility and its lower total radiation dosage. A conjunction class mission does have a relatively long timeline, but efficient use of torpor will reduce astronaut activity to only 65% of the mission duration, which will help reduce negative psychological effects. We'll discuss the technological readiness of torpor later on. Assuming all development proceeds according to schedule, the first launch episode occurs in mid-2033, sending the Mars Ascent Vehicle, Surface Habitat Rover, and Intercom satellite to prepare for the surface mission. Then, the second launch episode in mid-2035 takes the crew to Martian orbit along a fast transfer trajectory. A similar fast transfer will be used to return to Earth. Upon arrival, the orbiting habitat, or OHAB, will directly insert into a one-sol, highly elliptical orbit. Analysis showed that only an aerosynchronous orbit will provide high line-of-sight coverage of the landing site, which makes communication simple. At the same time, a low periaps is desired for orbit insertion. These two requirements define the eccentricity of the orbit, and its inclination is defined by the landing location. This synchronous orbit achieves 61% coverage of the landing site, starting before local sunrise and ending after sunset. During the night, Intercom, which is a satellite modeled after NASA's MAVEN, will maintain the communications link. Now, the surface mission occurs a full year after arrival at Mars, and various perturbations will cause the OHAB's orbit to precess dramatically in such a time frame. Therefore, the initial orbit will be planned such that after 1 year, the line of apsides will pass directly through the landing site at local noon. The full year in orbit before the surface mission is advantageous because it gives the MAV more time to conduct ISRU fuel production and allows for extensive landing preparation and science data collection. During this time, the SHAB will be deployed and driven remotely using real-time virtual reality to assess landing site conditions. A plethora of science experiments will be stowed within the orbiting habitat and conducted before and after the surface mission. For example, a high-resolution camera combined with a laser altimeter will help better map Martian topography for future landings. Another experiment will help fill a gap in Martian atmospheric data using a fleet of small powered gliders. Deployed every few weeks and piloted by the astronauts on orbit, these gliders will slowly descend through the atmosphere, collecting long profiles of data to improve models back on Earth. The capability of being piloted in real time greatly prolongs their lifespan. Furthermore, any extra mass margin on the OHAB will be delegated to outsourced CubeSats, which will also be deployed once in orbit. During the surface mission, all orbit operations will be paused, other than remote driving.
Entry, descent, and landing consists of 4 phases and is the most dangerous part of the mission. Directly entering on a steep trajectory and at 5.7 kilometers per second, the uncrewed MAV and SHAB will experience roughly 15 Gs of peak deceleration. The crewed MDV, on the other hand, will enter on a shallower trajectory at 4.5 kilometers per second to limit peak deceleration to a tolerable 6 Gs. An inflatable heat shield will be deployed for the entirety of the hypersonic phase, protecting against peak heating while guided entry is used to make trajectory corrections. Supersonic retropropulsion will take over 6.5 minutes later, after releasing the HIAD. Once subsonic, the lander will ditch the thermal payload fairing and underside cap, using the same thrusters for subsonic retropropulsion. Finally, 2 kilometers above the surface, hazard avoidance will be used to guide the craft down to a soft landing 9.5 minutes after first entering the atmosphere. The technology readiness of HIAD and SRP. Our short-duration surface mission, set to occur in January 2037, allows for a relatively simplistic surface architecture and targets a window of favorable conditions. These include relatively low dust storm frequency, a one-way Earth communications delay of only 15 minutes, and a solar activity well below maximum. The 3 craft will land within an ellipse inside of Hargreaves Crater, chosen for its flat terrain, low elevation, and high scientific potential due to its location within the Neely-Fosse exploration zone. Once landed in the MDV, the crew will deploy diver while waiting to be joined by the remotely piloted SHAB. Then, they will set off on a 1,200-kilometer journey across Neely-Fosse, traveling in a circular pattern so as to never stray more than 200 kilometers away from the MAV. They will explore 6 regions of interest along the way, periodically deploying diver to further explore difficult terrain. On the last day of the surface mission, the astronauts will return to the MAV, pack all samples into storage, and lift off into a highly elliptical orbit to dock with the OHAB. The decision to use a mobile habitat over a stationary one for a short surface mission represents a major design trade. It was decided that the additional scientific potential offered by mobile habitat outweigh the additional complication and risk. Consequent mitigation strategies touched on later include functionalities of diver and the MDV. To facilitate future missions, the SHAB will be remotely driven to the next landing site while the astronauts remain in real-time contact with it for the last 3 months in Martian orbit, and the ISRU plant will be switched back on to produce contingency locks that could be used in a future mission's emergency. In order to effectively search for life, biosignatures that characterize past or present life will need to be identified by searching for precursor and biogenic compounds, morphology, and gases. A holistic study of Mars's environment is also needed to better understand hydrology, geology, and climate as they relate to life. Detecting past biosignatures is challenging because they degrade quickly in the Martian environment and are often mimicked by abiotic phenomena. However, Neely-Fosse has favorable conditions to mitigate these complications, and as such, a high potential for harboring biosignatures. First, it has large quantities of fluvial sedimentary clay and impact glass, which on Earth harbor microbial communities and likely preserve past biosignatures effectively. Second, the abundance of steep canyons in the area increase the chance of finding recurring slope lineae, or RSLs, containing water and potential life. Third, Neely-Fosse's diverse geologic history includes volcanic, fluvial, and tectonic activity. This allows scientists to constrain the geochemical conditions around life's potential formation and detect it with more certainty. Fourth, elevated atmospheric methane concentrations in this region could be biogenic in nature and will be monitored for periodic fluctuations. Additionally, passing through Jezero Crater will also allow the crew to follow up on scientific discoveries made by the Perseverance rover. Many drilled core samples will be brought back to Earth to take advantage of more effective lab analysis in the hopes of finding biogenic minerals, morphology, or isotopes. An interesting novel experiment on Mars would be a surface network of seismometers, present on the lander stages and SHAB. This would provide the capability to triangulate the origin of Mars quakes and glean insight into the planet's weak tectonic activity.
An extended surface stay on Mars requires a good base of operations which will protect the crew and facilitate the mission's science goals. The Surface Habitat, or SHAB, will serve as the mission's surface operations base. Its extendable design allows a larger rover to fit within the launch fairing. The rover will remain stowed on the lander stage until just after the astronauts arrive in Martian orbit. During the deployment process, the SHAB will unfold its wheels, drive down a ramp from the ladder, and then extend into its surface configuration. In this form, the front module will dock with the main cabin, forming an airtight seal, and the rear bed will fold down. After 1 year of remote operations, the astronauts will descend to the surface. Now pressurized, climate-controlled, and with an ample 14 meters squared of floor area, the SHAB will serve as their mobile habitat, science station, power source, and storage unit as it traverses around Neely-Fosse for 30 days. During transit, 360-degree cameras strategically placed around the hull will enable the orbiting crew to safely pilot the SHAB for most of the surface mission, which will help relieve stress on the surface crew and free them to perform excursions. Each of the SHAB's 6 wheels individually articulate and are driven using dynamic isotope power systems for a top speed of 10 km per hour over flat ground. The suspension and all-wheel drive will allow this rover to climb 10-degree inclines and obstructions 1 meter tall. Both the reliability of the power system and the intelligent wheel design will help increase the longevity of the SHAB to enable its use during future missions. As the main hub for all science activities on the surface, the SHAB is well equipped with experiments and instruments. Most important among these is the drill and ground-penetrating radar combination. Mounted beneath the center module, this subsurface imager will capture millimeter-scale details up to a depth of 2 meters. Its output will be scanned by software that alerts the crew when interesting features are found. By optimizing the drill sites, the obtained core samples will yield the most interesting data possible. These will be acquired using a rotary coring barrel drill, which will descend 1.5 meters over the course of at least 1 hour. The core samples will be carefully sealed and stowed, not to be analyzed until they return to Earth. Aside from drilling, the surface crew will run experiments both within the SHAB center module and from the rear bed. Inside the rover, plants and cultures will be grown, assessing the hospitality of Martian soil. Other sensitive experiments can also be conducted within the SHAB. The modular science bay in the rear bed will contain various instruments that can be detached and replaced in follow-up missions. While only in use for 30 days of the mission, the SHAB has the very important task of protecting the surface crew from the Martian environment while still enabling science operations. Suit ports on the rear wall allow fast entry and exit of the habitat, reduce the risk of planetary contamination, and reduce gas loss to the surroundings. The exterior instrument suite mitigates the risk of contaminating the humans with Martian soil samples as they can be tested outside. The SHAB interior is zoned into living and science quarters to help psychological health and focus. Strong filtration, radiation protection, and other life support systems are necessary to keep the surface crew healthy during their mission. Some of these will need to be installed by the astronauts after their first entrance into the SHAB. Finally, a quarantine protocol similar to that of the Apollo era will be followed upon arrival back to Earth.
The orbiting habitat, or OHAB, in which the astronauts will reside for the majority of their mission, features a habitable volume of 75 cubic meters and is constrained primarily in width to fit inside the Falcon Heavy fairings, resulting in an internal layout with 4 levels. The OHAB's solar panels generate 10 kilowatts of power, and additional fuel cells and batteries will power the module during Mars eclipses. This torpor-enabled habitat also includes a consumables-lined storm shelter in the lowest level where the torpor devices are housed. During the transfer to and from Mars, the crew will assume a staggered stasis schedule, shown here. This schedule keeps 2 astronauts awake, rotates pairings, and will provide a steady awake stasis rhythm for 60-day periods. While in orbit around Mars, the schedule is modified to keep 3 astronauts awake, increasing the science output. Altogether, this implementation of torpor achieves a 20% mass reduction in our orbiting habitat. To protect our astronauts from radiation during this long-duration mission, the OHAB is outfitted with polyethylene shielding. Astronauts will also have access to personal radiation protection garments and vitamin C to mitigate radiation exposure during large solar particle events. Further, bioprotective drugs will be administered along with dietary antioxidants to reduce the risks of negative radiation effects. Losses in bone density, muscle atrophy, and cardiovascular capacity will be combated with prescribed daily exercise for our active crew members. Crew members in stasis will have neuromuscular electrical stimulation implemented to further reduce the atrophy of muscle. Psychological and psychosocial issues that astronauts experience due to chronic exposure to stressors will be monitored through the onboard integrated healthcare system. The VR system for driving the SHAB will also address mission monotony and provide restorative effects for our astronauts, and will be capable of delivering continued crew training throughout the mission.
The lander stage design was kept constant across all 3 landing craft to keep development costs to a minimum. Each lander stage features a cargo bay and a modifiable payload interface to attach all 3 payloads. The heaviest payload is the MAV, and as such the HIAD, fuel tanks, and descent engines were designed to handle its ballistic coefficient, delta V, and thrust requirements respectively. Conversely, to land the 2 lighter payloads, the fuel tanks only needed to be partially filled. A contingency of at least 25% is available to account for mass growth during each payload's development. Due to the necessity of using ISRU for the MAV, Methalox was selected as the ascent fuel since its high mixture ratio allows for a small mass of liquid methane to be transported from Earth, while the liquid oxygen can be produced from carbon dioxide in the Martian atmosphere. Solar power was chosen to meet the needs of the energy-intensive ISRU process due to its technological readiness and safety advantages over nuclear fission power. Since half the power generated during the sunlit hours must be stored to keep the ISRU plant running overnight, an impractically large solar panel area would be needed to produce all the required ascent liquid oxygen within the 3-year production window. Therefore, a more manageable production rate will produce 60% of the ascent liquid oxygen on the surface, while the rest will be transported from Earth. The MAV itself has a single-stage wide-body design that minimizes the structural mass ratio, lowers the center of gravity for stability, and reduces complexity. The design doesn't have any aerodynamic modifications since the air resistance is negligible on ascent. The cabin volume of 6.9 meters cubed was based on the Apollo lunar module with similar habitability requirements, and storage for 500 kilograms of surface samples is included for return to Earth. The MDV uses the MAV cabin design as a cost-saving measure, scaled up to 15 meters cubed. It is packed with extra consumables to support the crew for up to 2 weeks on the surface should they land farther away from the SHAB than expected. In this case, they would wait for the SHAB to be remotely driven towards them. Additionally, the suit port interface is visible on the cabin sides with rigid enclosures to shield the suits during EDL, and an extra suit included in the event of a primary suit failure. Finally, in its cargo bay, the MDV's lander stage carries diver and spare parts to be unloaded upon landing.
The diver will be a non-pressurized rover with a similar design to the lunar roving vehicle, used during day-long excursions to collect science samples and investigate areas where the SHAB may not be able to reach, such as up to 35-degree slopes with forest cells. While exploring the Martian terrain, diver will travel up to twice as fast as the SHAB. Additionally, diver is designed to shuttle the crew back to MAV in less than 10 hours during an emergency surface evacuation with speed of 25 km per hour. A primary feature of diver is its modular science bay, which allows the surface crew to easily transfer instrumentation from the SHAB to the small rover. Diver is also equipped with a container for surface samples and tools, emergency life support equipment, and an omnidirectional antenna that support communication. The OHAB is equipped with a high, medium, and low giant antennas that will allow surface and health data transfer with Earth using DSN's allocated S-band frequency bands. The SHAB parabolic antenna will allow high throttle-up communication with the OHAB. During Martian nights, the OHAB will maintain communication with the S-crew and SHAB through intercom, which will serve as a band pipe to relay this communication. Successful transfer of science data, reception of commands, and utilization of VR technologies may require parallel communication channels with different data rates. Finally, a major advantage of intercom is that it has a 25 years full supply, allowing its support for future Man on Mars missions.
These design specifics complement an integrated systems engineering approach. 11 total launches are required to bring all systems to Mars. Over half of these are exclusively for expendable propulsion modules, including the 2 SLS Block 1 launches. 9 of the launches use SpaceX rockets, continuing a commercial provider trend seen within NASA over the past decade and a half. Using the Falcon Heavy with an expanded center core provides twice the payload mass to low Earth orbit over a fully reusable stack, more than enough for most systems in this architecture. This mass margin, along with the low cost of commercial providers, ensures that even if payload masses increase or more Falcon Heavies are launched, the aggregate budget only grows by a small factor. Commercial providers are proving their reliability and capability with every passing year, and this mission takes full note of that. The mission lifecycle is split into 2 development and launch episodes. The first episode must develop at a slightly faster pace to be ready by 2033, which is acceptable because it doesn't include the most integral system, the OHAB. After the standard NASA development phases and reviews, all systems will eventually reach Mars, at which point the mission timeline combines both episodes. After the mission, the SHAB, MAV, and Intercom will continue their operations, preparing for follow-up landings. A small error was discovered in the technical paper, which omitted the MAV's ISRU operations, and has since been corrected. The budget was estimated using the life cycle cost estimation model, broken down into exploration systems, launch vehicles, and operations. This model estimates the cost of a subsystem through parametric equations and analysis of past spaceflight experience. Additionally, this model has calculation factors specifically for Mars vehicles. The cost was spread out by year based on the mission timeline and also to ensure the budget does not exceed NASA's projected budget for space exploration. The design, development, testing, and evaluation costs before the first launch were spread with a 60-40 model, and more budget was allocated to the launch episodes and surface mission operations. A 20% contingency factor was added to the overall mission budget to account for any budget overruns. The major risks to mission success were analyzed and categorized by using a likelihood consequence matrix. All risks that were in the red zone in the proposal have had mitigation strategies applied to them, and the resulting risk is shown. A number of mission design choices were made to reduce the number of critical failure points. One such event is if the SHAB is stranded far away from the MAV, requiring the implementation of diver. Similarly, should the humans touch down far from their designated landing site, the MDV is designed with 2 weeks of contingency consumables and life support. MAV ISRU operations have a built-in margin of 150 days of stalled LOX production due to dust storms and weather. Additionally, the lander payloads were reduced below the 22-ton limit to mitigate stresses on the HIAD and supersonic retropropulsion technologies. Finally, redundancy was added in critical equipment such as ISRU plants, fuel cells, and spacesuits.
4 technologies have been identified as mission critical, meaning that they represent a feature of the current architecture which cannot be replaced without drastic changes to the mission. These technologies have been carefully evaluated with their technology readiness levels and development plans to ensure readiness in time. Torpor has the lowest TRL, sitting at level 3, with current research focusing on animal trials and habitat design. The development plan includes expanded human trials starting in 2024 and cislunar space trials starting in 2028. Liquid oxygen ISRU, sitting at level 5, currently exists as a small-scale prototype MOXIE going on the Perseverance rover in 2021. Development challenges include ensuring long-term reliability and upward scalability to roughly 15 times MOXIE's production rate. The HIAD, sitting at TRL 4, has a 6-meter Earth entry lofted test slated for 2022 that will function as a proof of concept. Development challenges include improving manufacturing methods and structural integrity for a 20-meter inflatable toroidal design. Supersonic retropropulsion at level 4 is currently being used on Falcon 9 boosters upon re-entry. More computational methods to model entry flow will be needed to achieve stable retropropulsive exhaust. Methalox engines capable of supersonic retropropulsion will need to be developed and tested along with the HIAD in Mars-like entry conditions before use. There are also certain non-critical technologies being used in this architecture that are not yet fully developed. Technologies such as virtual reality driving, a rotary coring drill, and pilotable Mars gliders were included because they enable more scientific data to be collected. Similarly, technologies such as dynamic isotope power systems, EDL hazard avoidance, and suit ports were also included because they reduce mission risk.
While we are very happy with our design, there is at least one change we would like to make going forward. As a bit of an oversight, direct atmospheric entry was favored over Earth orbit insertion at the end of the mission. Recalculations showed that we were wrong, and an insertion into a geostationary transfer orbit only requires a small amount of extra fuel. Thanks to large mass margins, adding this fuel has zero impact on the overall architecture, and making this change will allow reuse of the orbiting habitat for follow-on missions. Our project has reiterated that a crewed mission to Mars will be extremely difficult. Sustaining a human presence on the surface will be even more complex, but the short and long term of Mars exploration look promising with various emerging technologies. Torpor, ISRU, an extendable mobile habitat, remote driving in real time, Mars gliders, new EDL technologies, and various other innovations will likely be not only useful but necessary for future deep space missions. Validating these technologies will be difficult, but their full integration into Mission Mars will lay the groundwork for future missions, and with experience, will eventually lead to a permanent presence on the Red Planet. However, before any emerging technology or mission architecture gets past the drawing board, it should make clear its emphasis on reusability. Follow-on costs must be reduced to justify this type of short-term mission, whether through infrastructure for future use, data gathered to enhance models, or overall lessons learned. Finally, the scientific understanding of our neighboring planet is currently our biggest motivator for Martian exploration, and as such, must take a front seat in design. Mission Mars takes all of these ideals into account, with the 3 goals of searching for life, returning the astronauts safely to Earth, and establishing a foothold for exploration at its greatest.